everybody. Thanks for holding out for the last keynote. I hope it meets your expectations or exceeds your expectations. So you actually undercut my introductory comments a little bit, because I was going to say to some extent that I've noticed that a lot of the talks and a lot of the discussions over the past few days have not completely, have not completely considered the human element. And there's a tendency to talk about how to build a better rocket, how to do something faster, how to concentrate on the technology and the engineering and the machinery. And I'm going to make a case that you ignore the human element, first of all, at your peril. That is, if you plan on sending people into space. We could debate whether you want to send people or automatic probes and robotic probes. I think that's a different discussion. I'm prepared to have that discussion, but probably not today. But at the same time, if you do accept that it's useful, meaningful, important to send people into space, you have to figure out how to accommodate them so that they can do their jobs. But also, part of it that's neglected that I hope to get to near the end of my talk today is the fact that the people become part of the system, part of the engineering and technical system. So if you want a resilient system that can repair itself in the face of unknown obstacles and anomalies during something like an interstellar journey, the people become a part of that. The people should not be an afterthought that you stick in after all the engineering design work has been done. You can take advantage of the fact that people are there and people are resilient and can take care of problems that are unforeseen when the spacecraft and the habitat are first designed. So it's a two-way process. So I'm going to start by saying that quote that some of you may have heard before: concern for man and his fate must always form the chief interest of all technical endeavors. Never forget this in the midst of your diagrams and equations. Of course, Albert Einstein was not talking about what we're talking about specifically, but I think it's a point worth keeping in mind. So with that, let me jump into some things that I think are relevant to the challenges that will be faced by crews and missions. Missions meaning the crew, the interactions among the crew members, the crews trying to accomplish their tasks, the crew interacting with the spacecraft and the habitat. I'm going to focus most of my talk on NASA's plans for Mars, understanding that it's a big extrapolation from what we're doing in the space station to Mars, and it's a huge extrapolation from that to doing anything beyond Mars in intergalactic space. Nevertheless, NASA has given a lot of thought, not only NASA, many others, given a lot of thought and promoted a lot of research on the Mars problem. And you can see here on the title slide that even though I'm at Johns Hopkins now and a faculty member in the School of Medicine, where I've been for about 31 years now, and before that, I was doing life sciences research in graduate school. So I've been in this business for quite a while. I took a 3-year leave of absence, and I was the chief scientist for the NASA Human Research Program, which is the organization that funds the research that is necessary to maintain human health and performance in long-duration spaceflight. If it sounds like I've memorized that phrase, it is because I have memorized that phrase. That is the charter, essentially, of the organization. Human health and performance. Again, this gets into the fact that you're sending people out there to do a mission, not just to keep them alive. Human health and performance in long-duration spaceflight. So occasionally, you're going to hear me regress and talk and say, we think this, or we're doing this. That's a throwback to some of my time at NASA. I am not representing NASA. Some of the things that I'm going to present are out of NASA documentation and literature. NASA can stand on its own 2 feet, can speak for itself. When I say we, I'm going to be talking more about the life sciences community, the bioastronautics community. Sometimes when I say we, I'm just going to be referring to myself. We can all sort it out later. So I think a couple of things that I think are going to be very relevant to this discussion that are somewhat remarkable. First of all, the fact that we send people into space so far for about up to a year. The Russians have had more experience with that than we have in the United States, but we've had a couple of missions on the order of 1 year to ISS, the famous one-year mission, which incorporated the twin study. It's a few years back, and that was 340 days. There are plans for more one-year missions to ISS to try to fill in the gap from 6-month missions, which is what's typically done on the space station, to a 3-year Mars mission. Now, currently, NASA's planning includes this little detour to go back to the moon. Extremely important to do that, to develop some of the technology and operations that you would need to go to Mars and beyond. But again, I'm going to focus a lot of my discussion on Mars. So it's remarkable that we can send people into space and expect them to accomplish anything useful, having evolved and developed in a 1G environment. In fact, they do that. So the second remarkable thing is that humans are extremely adaptable. It's amazing what they can do and how well they do. It's also remarkable, in some cases, the things that go wrong, and especially the ones that we don't yet know how to solve. I'm going to talk about those, obviously. Something that's almost as remarkable as those things is the fact that NASA is extremely transparent about almost all of this. Of course, they don't release private medical data. Sometimes that's where really interesting things are. But the things that I'm going to talk about, especially when they touch on NASA's plans, this is all on the NASA websites. Just do a Google search or your favorite search engine, NASA HRP, Human Research Program, HRR, Human Research Roadmap, and you will find pages upon pages of information on NASA's formal plans for addressing the kinds of questions I'm going to talk about. So with all that preliminary stuff, let me put this into a little bit of context. When we think about sending people out into space, to the moon, Mars, beyond, we're talking about progressively increasing independence from Earth. People in this room and online think about this a lot, undoubtedly, but not everybody really realizes the extent of this issue. Excuse me. Currently, we've got people on ISS. Typically, it had been 6 at a time. Now, of course, it's 7, now that SpaceX is flying somewhat regularly. Real-time communication with Earth, whether the astronauts want it or not. Houston is always looking over their shoulders, ready to lend a helpful hand. Evacuation capability, a matter of hours. If there's an operational problem or a medical issue, a medical emergency, the crew can get in a capsule, Soyuz or SpaceX now, hopefully Boeing soon, be back on Earth relatively quickly. We've never had to do that. But knowing that that capability is there influences the psychological mindset of the crews. So that relieves a huge amount of psychological stress, which turns out to be really critical. And strong consumables resupply, steady flow of cargo spacecraft going up to ISS, including taking things like medical supplies and fresh food once in a while. When you get out to the moon, near real-time communication, effectively real-time communication, a couple seconds delay, round trip. Evacuation capability gets a little bit more challenging. If there's a medical issue, like a traumatic injury on the surface of the moon, you got to think, do I want to get this person back to a proper gold standard level of care on Earth, if that means subjecting that person to the G loads of taking off from the moon and coming back doing re-entry on Earth? Maybe it's better to let them get second-rate care on the moon. Have to make those decisions. Hopefully, they've been thought of ahead of time. Limited consumables resupply because of the distance. Now, when you get to Mars, that's completely different. No real-time communication. One-way communication delay can be on the order of 20 minutes. One way. That's assuming that the Earth and Mars are not on opposite sides of the sun at the time, or other issues that may impair communication. So the crew is on their own if there's an emergency, including a medical emergency. Essentially no evacuation capability. This is something that's also important to keep in mind due to the orbital mechanics and propulsion limitations. Once a crewed human mission to Mars gets past a certain point, and I don't know what that is, it could be a week out or a couple of months out. Once it gets past to a certain point, it is going to Mars and is going to do its 3-year mission. Half the crew could die halfway through the mission. You have to wait until the planets are properly aligned to bring them home, or else you don't have the propulsion capability. So this has to influence your mindset in the planning, including the mindset of the crew. Somebody dies or gets an intractable disease 3 months into a 3-year Mars mission, Are you going to be using all of your medical supplies to keep that one person alive when you've got 3 or maybe 5 other crew members to take care of? You want to think of these things, and you want to make sure that all the crew members are on board with what the decision might be. So no evacuation capability, no consumables resupply. What you take or what you pre-position is what you have. This turns out to have implications for things like food and medicine because they have limited shelf lives. So I'm going to talk about 3 general categories of things. What are the issues? What do we know from experience so far? Humans in space. What are the troubling trends from those experiences? And what we just do not know. What's really out there on the edge, including what we don't know that we don't know. The unknown unknowns, the things that are going to come up and bite you because you solved all the known problems. So what we know is to a great extent, not exclusively, but to a great extent, due to research that's going on the International Space Station. Continuous human presence for over 20 years, pretty remarkable. And ISS is a pretty busy place. The last time I heard, and I think this is still true, except for routine operations and maintenance, the biggest user, the biggest single user of crew time on ISS, crew time being the most valuable resource, biggest single user of crew time is the NASA Human Research Program, because NASA recognizes this is why we're sending people into space for long periods of time on ISS, to figure out if we could send them into space for longer periods of time somewhere else. So these are just pictures of some examples. NASA websites are full of these things. Down on the bottom, you see somebody doing undoubtedly an HRP experiment, a cycle ergometer, measuring gas exchange, wearing some electrodes. The upper 2 pictures include Scott Kelly, who was on the twin study in the 1-year mission a few years ago. On the right side, he's giving himself a flu shot. Why is he doing that? They're not worried about getting flu in space. That is a titrated perturbation challenge to the immune system. That was part of the twin study. His twin brother, Mark Kelly, who stayed on the ground, did the same thing. He probably had a doctor or a nurse give him the injection, but basically the same procedure. And on the left-hand side, for reasons that I will go into in a few minutes, Scott Kelly is getting an ultrasound examination of his eyeball. Turns out that that's a really critical issue. So NASA looks at things this way, and not only NASA, but generally most space researchers in the life sciences, in terms of 5 overall hazards. The hazards are the physical things, physical and operational things that happen in space. They lead to a particular set of risks. So you have to follow me on the nomenclature, at least this is what NASA uses. So the system hazards, distance from Earth, obviously, that's remoteness, that's autonomy. Hostile and closed environment, you close the door and nobody gets in or out. If you have funguses growing behind cabinets, if you have toxic substances, if you have outgassing, yeah, those are going to be troublesome. You can't just open the window and air out the accommodation. Isolation and confinement. This turns out to be really interesting. These are the psychological issues of a small number of people in a small space for a long period of time. Now, this is a fairly large room compared to a Martian spacecraft. Nevertheless, look around the room, find 3 of your favorite people here. Everybody else leaves the room, close the doors, nobody gets in or out for 3 years. Yeah. That's what we're talking about with isolation and confinement. You might be good friends by the time that mission starts, but by the end, if your buddy's chewing with his mouth open, you're going to kill him by the time you're finished. We have to accommodate this. This to me was really interesting when I spent time at NASA. I'm a biomedical engineer by training. Even though I do sensorimotor neurovestibular research, I take a kind of rigorous mathematical engineering approach to that. What I'm going to say, it's not derogatory term, this kind of soft sciences, the psychology, the interpersonal relationships, teamwork, it turns out to be absolutely critical, and it infuses everything else. So this turns out to be really important and really interesting, much more interesting than I had anticipated. Space radiation, we'll get to radiation. I'm not going to talk about radiation very much because radiation is a bit of a mess frankly, in terms of getting a handle on how bad the problem is. And altered gravity, this is the one we tend to think about in terms of long duration spaceflight. Standing here in a 1G environment, I'm constantly loading my muscles, my bones, challenging my cardiovascular system to maintain perfusion, blood to the head. You go into a 0G weightless environment. You don't have that challenge. You don't have that constant challenge. Astronauts on ISS exercise about 2 hours a day, at least 6 days a week. That's a lot of exercise when you have 6, 7 people on the space station. Some of those countermeasures, those exercise countermeasures have been pretty effective. Nevertheless, there are some other issues. Key point being, all of these things get worse with time. So none of these are really inherently self-limiting. Okay, so this is a pretty big deal and it leads to a number of different issues. This is how NASA looks at this problem. So this is freely available on the NASA website. This is something called the Integrated Path to Risk Reduction, the PRR, Path to Risk Reduction. And this is where NASA, being the Human Research Program, being a biomedical research program, looking at the soft pink squishy things, humans that you send into space, embedded in a highly technocratic engineering operational organization, which is largely what NASA is, rightfully so. They build rockets essentially. But to convey the complexity of the life sciences, human variability, very difficult for people in the physical sciences sometimes to grasp the complexity of biological and physiological processes, NASA uses this chart. So down the left-hand side, it's a bit of a useful fiction. Down the left-hand side, there are the main risks that have been identified. So things like radiation effects, what NASA calls BMED, behavioral medicine, that's the psychology, psychiatric aspects, variety of things related to 0G exposure, and it's a timeline. And NASA does a very rigorous and sometimes very contentious process of assigning a color to these based on likelihood and consequence. If it has a high likelihood and it's going to kill you, then it gets a red rating. And NASA's job, HRP's job, is to do the research to take the red things, make them yellow, which means, okay, we're getting kind of comfortable there. We have to validate some countermeasures, and make the yellow things green, which means you're ready to go. Now, there's a couple problems with this chart. It's science on a schedule. That's what going from left to right is. So let's say it's a success-based strategy, which doesn't always work in any science, let alone the life sciences. Nevertheless, it's not a bad way to categorize these things and try to get a handle on how you would approach them with limited resources, limited funds, limited time, in this case, the lifetime of ISS, and limited crew time if the experiments require being done in space. So let's just talk about a few of the issues. Now, the slide that you're looking at now is usually the basis for my entire talk, and I can give multiple slides on each one of these. I'm not going to do that because I want to make some other points that are a little bit broader, but I'll talk about a few of these very quickly. Food and nutrition, I mentioned that. Food and nutrition turn out to be really important, not just for the obvious reasons, nutrition, but also on ISS especially, this is very apparent. Food is sometimes the only thing that the crew members are comfortable with. I mean, it is the comforts of home. It's what they're familiar with. And it's not uncommon, shouldn't say that. I'll say at least, I know of at least one case, and it's probably more broad than that, where the commander of an ISS crew insisted that we will have at least one meal together each day, and that will be dinner. That's when we're going to see each other and spend time together. What do you do? What's a bonding experience here at a conference or anytime? Holiday meals, family meals. Meal time is more important than just nutrition. You sit down and have a couple of drinks together. You break bread together, whatever the euphemism you want to use. So this is important. And you want to make sure that the food maintains its nutritional value, but also its palatability so that it's not a burden to get together and eat. Challenging for a 3-year mission. Kidney stones. One of the things that happens in space due to unloading of the bones, the body is very efficient and reduces the metabolic load where it's not needed. So starts to shed muscle mass, starts to shed bone mass, bone mineral density, calcium. That calcium has to go somewhere. Well, it goes into the urine and is excreted. It goes into the urine. Very interesting. What causes kidney stones? Calcium in the urine. Okay, so hasn't been a problem yet. Haven't had to abort a mission, but there are some troubling indications post-flight that kidney stones may be an issue. Human system interaction. This could be the basis of a whole conference. It is the basis of whole conferences. Crew interaction with the spacecraft and with the habitat. Trust in automation. Excuse me, shared mental models. Do you trust what the automated facility is doing for you? When I rent a car and then take it, turn it in, and then travel to another city and rent a different car, I'm thrown off for a significant amount of time because the automation in the previous car isn't the same as the automation in the car I'm currently driving. That's just a little anomaly for me. It's just a little clever thing that keeps me amused. On a Mars mission, it's a thing that's going to kill you potentially if you don't understand the feedback and the interaction between you and the spacecraft or the habitat. Pharmaceuticals, very similar to the nutrition and food problem. 3-year shelf life. What drugs do you have in your medicine cabinet that have a 3-year or longer shelf life? Oh, and can do so while withstanding radiation exposure in deep space. Immune system function. Immune system function is altered in ways that we don't completely understand in long duration spaceflight. Some of the examples are given there. Suffice it to say that there are some changes. Wow, what's one of the things that we might potentially be worried about? Well, we know that the virulence of some microorganisms, like Salmonella, for example, increases in space. Why? Why that one and not other ones? We don't know. We know at the same time that some aspects of immune system function decrease. They get worse over long duration spaceflight. So far, those two lines have not intersected with each other. Decreased immune system function and increased virulence. Are they going to intersect between 6 months and 1 year, in which case we might detect them on 1-year missions to ISS? Or is nature going to throw us a curve and are they going to intersect at 1.5 years, which we will not see until we start to send people to Mars, and it's too late to do something about it 1.5 years in? Or are they going to intersect at 5 years, in which case we won't see it until we're doing interplanetary journeys, perhaps? Changes in the microbiome, all those things, all those microorganisms that live in your gut, they're also on your skin. There's more of them. You've probably heard this phrase before. There's more of them than there are of you. There are more cells that form the microorganism that do not share your DNA than there are cells that make up your body. So these are really important, and they interact with the cognitive function, somewhat surprisingly, and a number of things, including, of course, digestion. Some aspects of microorganism function, microbiome function, are changed during long duration spaceflight. Why? Don't really know. Is it the fact that you've closed in the environment and you've reduced the normal exposure to a turnover in microbiomes that you normally get just by interacting with people and things outside, living organisms? Maybe. Maybe the answer is to just package up a bunch of jars of microorganisms from various people and animals and plants and open them periodically during a space flight to keep the immune system microbiome challenged. We don't know. Sleep. Sleep is disturbed on ISS missions almost routinely. Alarms are going off. Cargo vessels are coming up all times of the day and night. On longer missions, when you can get into a more routine, like something taking 9 months maybe to go to Mars, maybe this won't be such a problem. A lot of people, a lot of astronauts say they've never slept better than in space, while other people say that it's been a real challenge. Sleep medication, pain medication, two of the main things that are taken by astronauts in long duration spaceflight. And arrhythmias, heart arrhythmias, not so much of a problem yet, but it's one of those things that is extremely rare, happened on one of the Apollo missions, extremely rare, but has potentially dire consequences. You don't want to have a cardiac problem in an astronaut in space. Now, in addition to all those really interesting things, which are kind of space related, I mean, it's all physiology, right? But they're basically consequences of going into space. There are other things that are just consequences of being a human. So traumatic injuries, rashes of various kinds, all sorts of things, some of which get worse in space motion sickness due to neurovestibular effects. So NASA has put together something called the Exploration Medical Condition List, MCL. You can look this up online. And it is basically 100 things that NASA is saying, you know, you want a medical system for Mars or the moon? It has to address at least these things. So it focuses your thinking. Hopefully it addresses more than this. One thing very telling on this, what's circled there? Behavioral emergency. What's a behavioral emergency? Behavioral emergency is when you have no alternative but to duct tape one of your crew members to the wall because he or she is about to go crazy. Isolation and confinement. There are procedures for this in the documentation. As far as we know, have not had to have been invoked yet. Very interesting. This, of course, is a very sensitive subject. We don't, even on the research side, we don't hear a lot about what issues may have happened because that's medical data. But if you read between the lines in some of the astronaut autobiographies, you get some indications sometimes of maybe tensions developing. I'm going to get back to that point in just a minute. Let me, though, talk about two of the issues that I think are of particular interest. At least they got my attention. So one of them is related to the extended time in zero-G and weightlessness. This is what NASA calls SANS. They used to call it VIP, V-I-I-P, Visual Impairment Intracranial Pressure. So VIIP, just about the time everybody was finally memorizing what VIIP actually stood for, that NASA decided it's time to change the acronym. So now it's called SANS, Spaceflight Associated Neuroocular Syndrome. So are there enough vague words in there? It's spaceflight associated, which means we're not exactly sure what aspect of spaceflight causes this, probably the zero-G part, the weightless part. Neuroocular, okay. The eyes, the nervous system, some combination of that. A lot of ground in there, and it's a syndrome. It's a thing. Is it a disease? No. Is it going to kill you? Probably not, but it's troublesome. So here's the prevailing theory is that this is due to headward fluid shift. That part's not a theory. We've known forever, as long as we send people into space, that due to the lack of a hydrostatic gradient in space, due to lack of gravity, loosely speaking, a weightless environment, fluids are redistributed somewhat evenly throughout the body, which means that they shift toward the head. Blood, lymphatic fluid, glymphatic fluid, which is the drainage of waste products from the head and the nervous system during the night, usually. Cerebrospinal fluid, the fluid that surrounds the brain and spinal cord, all shift toward the head. And astronauts get puffy faces. And here's Story Musgrave on the Earth, and in space on the right, his face is puffy. Gives them sinus congestion, alters their sense of taste and smell, food and nutrition impact. Okay, so what happens? Well, you have an increase, again, this is the prevailing theory. Increase in intracranial pressure, an increase in the pressure of the fluid surrounding your head, kind of like a mild form of hydrocephalus, water on the brain. So what's the relief valve for an increase in cerebrospinal fluid, an increase in the fluid pressure around the brain and spinal cord? Well, it seems to work its way down the sheath of the optic nerve. Now, you might not know what that means anatomically, but it certainly doesn't sound good. Right? It works its way down the optic nerve to the back of the eye and impinges on the back of the eye and causes what's called globe flattening, which is like pushing on a beach ball, causes the eye to flatten, changes visual acuity because you've changed the optical properties. This is how it was first noticed. Astronauts were coming back saying, my acuity, I can't read my checklist. I'd go, well, okay, you've been in space for whatever, 6 months. You're 6 months older and you were middle-aged to start with. So, you know, this is not unexpected. Yeah, it's more than that. It's a real visual problem. And then when people started looking more carefully, they started to see retinal changes, retinal damage, some changes that don't seem to reverse after return to Earth. This is not, problem is not ubiquitous, but it's fairly extensive. It's seen in a lot of people. So you can see down in the bottom chart, an example of globe flattening at the very bottom. It's been augmented, obviously, but those are MRI images from before flight. Excuse me, on the left-hand side, and in flight on the right-hand side, you can see the flattening of the globe. It's a little more oblong. These are obviously done with MRI before and after flight, since we don't have an MRI in space. So this is important not only because of the vision changes, right? Screwing around with vision in high-performing individuals in a very challenging and demanding environment, yeah, that's the kind of thing that gets people's attention. So this is a significant problem. On the other hand, it hasn't caused blindness yet. We don't know if this is self-limiting. Is it continue to get worse on longer and longer duration missions? Will it be mitigated by the equivalent of lunar gravity? So can we have people on the moon for long periods of time? Is 1/6 G enough to maintain the fluid distribution more properly? We don't know. The other thing, though, we noticed some other changes. There are, I won't go into detail. The slide is from a paper. It's online, freely available. There are some indications of slight changes in the neurons in the brain due to this extended period of slightly elevated intracranial pressure. Well, now we're really talking about a potential problem. Are you going to have cognitive changes in deep space missions of extended durations due to the shifting of fluids? Space is already a pretty challenging environment. You don't want to be impeding cognitive function. Okay, so enough of that. Let's say that is under significant study at the moment. Now here's the other one, going back to what I was talking about before, the psychological aspects. This is from a fascinating study called the Journals Project. Jack Stuster was the PI. The final report is available on the NASA website. So look for Stuster Journals, and this is just what it sounds like. For the period of this study, those astronauts who agreed, did all the consent, signed all the forms, agreed to participate, filled out journals while they were in space on a periodic basis, once a week, once every other day, I don't know what it was. And you know, it's a journal. They can talk about whatever they want to talk about. The text is downloaded to a very secure server. The PI goes through and does some automated analysis, figuring out what are the things that the astronauts are talking about during, in this case, up to 6 months on the space station. Well, it's a very enlightening reading. It turns out exercise and food are something that they're very concerned about. But if you went one step further and extracted journal entries on conflict, words that indicate that the crew or the crew and ground control are not really getting along as well as they would like. Or on the right-hand side, group interaction positivity ratings. You take the good things like, hey, this is exciting, I'm having a great time up here, peak of my career, and subtract the negative things like, I'm going to kill my crewmate because he's eating with his mouth open all the time. And in both cases, the trends are not really promising. So this is divided into quarters of a 6-month mission. And in particular, now we don't know if are these trends, are they going to continue? Can we extrapolate based on these? Are they self-limiting? Are the indications here of any significance? We don't know, but what's a little bit troubling is that they don't match the temporal changes that we know from other studies of people in stressful situations, like maybe sitting in a conference talk like this one. There's something called the third quarter effect in many of these conditions. Third quarter effect is being a junior in college, right? The first 2 terms, first 2 years, very exciting, meeting new people, doing new things. Senior year, very exciting, light at the end of the tunnel, you're about to finish. That junior year, you know, you're just slogging through. It's like where you were about maybe 5 or 10 minutes ago in this talk. You thought it was going to be the greatest thing in the world when I first started. About halfway through, you realize that maybe it's not that exciting after all, but it's not yet the end in sight. Well, now the end maybe is in sight, so we're in the 4th quarter. But anyway, this has been found for a huge number of things, as long as people know how long the thing lasts. An hour lecture, a 6-month mission, wintering over in the Antarctic. ISS time does not follow that trend. Should we be concerned about that? I don't know. But here are some troubling things. Like I said, sometimes you don't really have to read between the lines to get an idea of what these issues are. So this is from the personal journey of the cosmonaut, Valerie Ryuman. All the necessary conditions to perpetuate a murder are met by locking two men in a cabin of 18 by 20 feet for 2 months. 2 months. Now, that was small. That was the Salyut space station, I believe, not even Mir. So that was a really small space for a long time. And the bottom one, which I'm not going to read, is kind of an official NASA statement. It was from something that at the time was called the Bioastronautics Roadmap. Now it's the Human Research Roadmap. This is defunct. So I'm afraid you can't find this particular phraseology on the official NASA website, although you can find it on some blogs and things like that. But suffice it to say that people are making the case that there are some troubling indications in terms of interpersonal relations, teamwork, people getting along, possibly a troubling trend. Radiation, I'm not going to talk about radiation. Depending on who you talk to, and this means radiation researchers, it's either the worst possible thing you can imagine, and it's going to kill people, and we have no right sending people into space for long periods of time with our current state of knowledge, or it's no problem at all. And these are the research people, some in the research community. We've never had to abort a mission because of radiation. We've never had a medical problem directly attributed to radiation. Okay, we haven't been in deep space beyond low Earth orbit for such long periods of time. Nevertheless, radiation, NASA is revisiting and revising its stance on radiation, focusing a lot more on countermeasures rather than just characterizing the problem. This is a work in progress, but suffice it to say that. Okay, so troubling trends. Interesting one, deep vein thrombosis. Deep vein thrombosis is a blood clot in the veins coming from the head. This was found in a mission, ISS mission, about 2 years or so ago. Now you can look at this and say, deep vein thrombosis, we've been sending people into space for 60 years. And we've never seen this before. This isn't fair. Well, why is nature doing this to us? Well, this is exactly what I'm trying to get at. What's the unknown unknown? This was found not through medical screening on ISS. This was found during ultrasound during a research study. This person is potentially lucky to be alive due to the research study. Now, what do you do with deep vein thrombosis of the blood clot that might lead to a real medical emergency in space? Do you treat it aggressively with the limited supply of anticoagulant that you have on board? Or do you titrate the supply so that you can extend it until you can get a cargo resupply up there? Turns out they were able to call for help on Earth and get some insight. You're on Mars, don't necessarily have that advantage. Okay, so clinical decision support, there should be some automated procedures on board to help people make that decision. Let me end with one major point. What's next? Deep vein thrombosis, some aspect of psychological issues, neurological or cognitive problems due to the fluid shifting. We don't know. That's the essential point. So we have to not only mitigate the known risks, but also have a plan in place to look at the complexity of the entire mission. This is captured in a chart that is called the contributing factor map. This is not my work. This is work of Jennifer Mindock in her doctoral thesis at UC Boulder a few years ago. But this is a compendium of all the factors, all the ones that she could think of, and going through the literature, it's been vetted, all the factors that contribute to the success or potentially the failure of a long duration human spaceflight. And they include not only the physiology and the psychology, but working up that list, the way you design the mission operations, crew scheduling, time commitments, crew training, the way you design the spacecraft, personal space, workspace, reconfigurable space, habitat considerations, interaction with the spacecraft, user interface design. All these things interact with each other. If you're having a hard time finding a quiet place to get away from your crewmates, that's impacting your psychological well-being, which is probably going to impact your immune system function and cardiovascular function. We know that from ground studies, which is going to impair your ability to do your job. Part of doing your job might be to maintain the habitat in the spacecraft, which means then you've further impaired your ability to reconfigure the space and maintain the spacecraft. So by the time you've got that done, you've got this great intermixing of complex interactions that turns this into a complex network. And my final point is that hopefully we can draw on some findings from complex network theory, complex systems theory, to help us characterize the almost unimaginable complexity that comes from defining the interactions between these components. That, I think, is where there is a huge need for research to look at mission resilience, which goes beyond just mitigating the problems that you know you're going to have, but also building in tolerance and resilience so that when the unexpected happens, the mission does not come to a crashing end. So with that, thank you for your attention.
Great. We're going to stretch time a little and do a couple of questions. We've had several from the audience, so go ahead.
Thank you. I've got a couple of questions here, which are essentially aspects of the same question, I think. So let me read them both, and maybe you can respond to the overall issue. Astronauts have 20/20 vision. With vision changes due to zero-G occurring, has NASA looked at whether near or far-sighted individuals might have better functionality? And what's the current understanding of the role of subclinical health conditions such as insulin resistance in the presentation of the health issues of spaceflight?
Yeah, two great questions. So obviously the first one is a little tricky, right? Do you want to start sending people with known, vision change, myopia, hyperopia is not going to kill you, but you've kind of crossed a line when you start to say, we're going to start sending people with known deficiencies, anomalies into space because the spaceflight environment will tend to counteract them. There are some people, well, at least one, who used to hound me a little bit during my time at NASA, who think that we should be sending people into space for long duration flights who don't have legs, either through a developmental anomaly or amputation, because that's the fluid reservoir. That's where a lot of the fluid comes from that shifts to the upper body. And you don't really need the legs in space. They just get in the way. So you reduce volume requirements, a lot of things. Now, there's some ethical issues in an emergency. You would still like to have your legs when you land back on the Earth. So I would say that it's an intriguing idea, but I'm saying that it's probably not considered very seriously by NASA because the job should be to maintain peak function, not to kind of throw in the towel and say we have no recourse, but to admit that this is a problem we can't solve. But let's leave that possibility open. And the other one is subclinical issues. Subclinical issues that's a really interesting topic on its own, because the problems with immune system function, I've asked my colleagues who do the immune system work this a couple of times. If there are changes in the immune system function in long duration spaceflight, and astronauts come back from 6 months to a year on ISS, and after spending time in the medical tent, coming back from Kazakhstan, what do? They land at Ellington Field in Houston, and they are immediately embraced by their families, including these little bags of germs called children. Right? And yet, we don't hear a lot of reports of astronauts coming down with contagious diseases of various kinds immediately after their return. So what's going on? The immune system is, well, I don't know, altered at least by long duration spaceflight, but apparently not altered enough for this to be a problem. So it's subclinical alterations. Subclinical alterations are really tricky because you can say they're subclinical. We don't have to do anything about that. Well, if you're on Earth, maybe you don't have to do anything about it, because if it does cross a clinical threshold, you can just go to see your doctor. If you're in space, maybe the subclinical threshold is giving you an early warning that you want to do something about it. So this is the idea of taking a systems approach, being proactive about developing problems. On yet the other hand, you can't track and mitigate every potential problem. especially if it's a subclinical problem for which you don't have evidence that it's going to lead to a real problem. So these kinds of systems issues are really intriguing, and they're real cost benefit calculations that have to go into them.
How much training in medicine do astronauts receive so they can treat one another? And how much can they rely on Earth communications? And additionally, should medical supplies be set up for each individual astronaut specifically? And are space preparatory labs in development or have been developed to alter the human physiology?
Okay, so let me see if I can address all those issues. They're
And you got
not-
to do it in 60 seconds.
Yeah, exactly. I know. Not every mission has, so every mission to ISS has a crew medical officer. I don't know the number of hours, but they have medical training, limited medical training. You would not want one of these people taking out your appendix in space, but you might be happy, satisfied at least, with one of those people taking out an abscess tooth in space. So, you know, there's a limit. The NASA guideline at the moment, or regulation, is that missions over, I think it's 270 days, something like that, the crew medical officer must be a physician. And there are physicians in the astronaut corps. But as one of them, Serena Anand Chancellor, has said, I'm not an astronaut dash physician. I'm an astronaut. I happen to be a physician, but I'm not going into space to be a physician. I'm going to space because I'm an astronaut. Okay, guess what? You're the crew medical officer, so now you are responsible for the crew. Okay, when's the last time you did an intubation? When's the last time you set a broken bone? When's the last time you did any one of a number of medical procedures? Years, because of the crew training, it's required to be an astronaut. So there is some level of medical care. Yes, astronauts, of course, when they're in low Earth orbit, and also on the moon, will have immediate and very useful interaction and communication with doctors, psychologists, psychiatrists, and people on Earth, obviously, of course. Autonomy increases greatly when you get out to Mars and beyond. And I forget, fortunately, I guess I forget the last part since I'm running out of time, but personalized. We're moving in that direction. NASA is showing more interested in the omics, genomics, proteomics, metabolomics, personalized gene expression profiles, including epigenetics, how the gene expression has changed due to environmental stressors, which will hopefully lead toward personalized countermeasures. Maybe not everybody needs to exercise 2 hours a day in space. That would be a great relief. Maybe some people need to exercise more than that. So countering the countermeasures, this should not be, my last soapbox point, this should not be treated as a population statistics problem. You're going to send 4 or 6 people to Mars. That is not a population in the sense that an NIH study is a population study in terms of public health issues. Each one of those individuals has to be treated as an individual. So that question picked up a crucial point. We're not there yet, but we're moving there.
Mark, that was great. Thank you very much. We appreciate it.